You know, every time you play a game, your graphics card is pulling off what is basically a high-speed magic trick. Well, today, we're going to pull back the curtain on the final and, you could argue, the most important part of that trick, the output merger. It's the real unsung hero that decides what you actually get to see on your screen.
I mean, it seems obvious, right? But how does a computer, which is really just looking at a sea of ones and zeros, know that a solid wall should block your view of a character, but a pane of glass shouldn't? This question, right here, gets us straight to the heart of what the output merger actually does.
The answer all comes down to a component that acts as the screen's final gatekeeper. Seriously, think of it like the last checkpoint, the final line of defense, before any single pixel gets the green light to appear on your monitor.
Okay, so to get a little more specific, a GPU works with these things called fragments. You can think of them as candidates. They're all hoping to become one of the final pixels you see. The output merger is the stage that looks at every single one of these candidates and makes a ruthless split-second decision. You're in, or nope, you're out. And honestly, this is the best way to picture it. Imagine your screen is this huge, exclusive nightclub. The output merger, it's the bouncer at the front door. It's got a super strict guest list, a set of rules that are absolutely non-negotiable. And it checks every single fragment trying to get in, millions and millions of times every single second. It's just insane.
So, what's on this bouncer's job description? What's its mission? Well, it's not just about letting things in or kicking them out. It has some very specific, critical responsibilities that literally make or break the final image you see.
All right, here's the rundown. First up, visibility management. This is the big one, making sure that wall actually hides the player. It's fundamental. Second, color integration. This is how you get those beautiful see-through effects like water or smoke by perfectly blending colors together. Third, data storage. It's got to put the final approved pixels into exactly the right spot in memory. And finally, filtering. Basically, cleaning up the image to prevent any weird visual bugs.
Okay, so let's follow one of these fragments as it tries to get past our bouncer. It has to survive this intense, multi-step inspection process to prove it belongs on the screen. It's not easy.
This is the gauntlet every single fragment has to run. First, there's a stencil test, which is kind of like checking if you're in a special, VIP-only area of the screen. Then, the absolutely crucial depth test. After that, color blending for anything that's see-through. And only if it passes all of that does it get the final write into memory.
Let's really zero in on the most important step for making a 3D world feel real: the depth test. The entire test, all the complexity, it boils down to one simple, incredibly powerful question. Out of all the things trying to take up this one pixel of space, which one is closer to the camera?
And the way it figures this out is surprisingly straightforward. The GPU just looks at the depth value, the distance, of the new fragment trying to get on screen. Then it compares that to the depth value of whatever pixel is already sitting in that spot from a split second ago.
And the logic is just beautifully efficient. If the new fragment is closer, it wins. Simple as that. It becomes the new pixel, and its distance gets recorded. The old one, gone, thrown out. And if the new fragment is farther away, it's immediately discarded. This one rule, applied billions of times a second, is what creates the entire illusion of a solid, three-dimensional world. But what if the object isn't solid? What if it's glass or water? That's where color blending comes in. If a fragment is from a piece of glass, it doesn't just replace the pixel behind it. The output merger has to do some really fast math to mix the new fragment's color with the color that's already there, and that's how we get that seamless see-through effect. Now, to do all this super fast inspecting and sorting, our gatekeeper needs a toolkit. It can't just keep all this information in its head, right? It relies on a few special areas of high-speed memory called buffers. So here's the toolkit. First, you've got the depth buffer. You'll often hear it called the Z buffer. This is the bouncer's 3D map of the entire scene, keeping track of exactly how far away everything is. Then there's the stencil buffer, which is like having a set of precise stencils to mask off certain areas so they don't get drawn on. And finally, the color buffer. That's the canvas itself, where the final, approved pixels are painted to create the image you actually see.
So, this system is incredibly fast and incredibly precise, but it's not perfect. And when our gatekeeper gets confused or the data gets a little messy, we start to see some very specific and often very annoying visual glitches that can just totally break the immersion of a game.
The most famous of these glitches is something called z-fighting. This is what happens when the depth buffer just doesn't have enough precision to tell which of two surfaces is closer. They're so close in distance that their depth values are practically identical, and the system just can't make up its mind.
Oh, you've definitely seen this. Ever see a texture on a wall or maybe a decal on a car just flicker and shimmer like crazy? That is z-fighting. The output merger is literally flipping back and forth every single frame, unable to decide which one wins the depth test. It's our bouncer getting totally flustered, and it just shatters the illusion of a solid world.
And beyond glitches, this whole stage can be a huge performance bottleneck. Overdraw is a massive one. That's when the GPU wastes a ton of power perfectly shading, say, a character that ends up completely hidden behind a wall anyway. All that wasted effort is what can make your frame rates drop. And at high resolutions like 4K or 8K, just moving the insane amount of data to and from these buffers can create a data traffic jam, slowing your powerful GPU way down.
So, at the end of the day, the crucial point is this. The output merger is the absolute unsung hero of 3D graphics. It's the final quality control, the silent bouncer, making billions of tiny, instantaneous decisions that are absolutely essential for creating the stable, believable worlds we love to explore on our screens.
Without it, everything would just be a chaotic mess of pixels all fighting for the same spot. So the next time you see a flawless, beautifully rendered scene in a game, just take a second to remember that invisible gatekeeper, the output merger, working tirelessly behind the scenes to make it all look just right.